I may introduce the first speaker of this session, Paul Larson, from Miami University, Ohio. And the title of his talk is Scott Processes Revisited.
Revisited, yes.
Yes.
Okay, thank you.
Please go ahead.
All right, let me try to share the screen here, and then just did this a second ago. So, okay, I hope everyone can see it. So thank you very much. It's my pleasure to be part of this meeting. Very happy to be here for it. I'm not happy that I can't be in Kobe for it. I wish I could be in Kobe, and I hope to be in Kobe soon. And I hope to see you, Sake, when I come. This is a topic that, of course, you and I discussed. I was just looking at the emails. I guess you came to Yamaguchi. We talked about this in 2014, I think. And I was looking at the emails, and I saw that I put a bunch of questions in the emails, and a lot of them are in this talk too. So a lot of those questions are still open. Okay, so this is a project that I started, I don't know, around 2011, 12. I did the big chunk of the work actually at the Fields Institute program on forcing in fall of 2012. And the paper eventually appeared, or a paper eventually appeared in this volume edited by Jose Urbina, Beyond First Order Model Theory. I think that's 2017. Most of what's in this talk is older stuff, and there's a couple new things I'm going to talk about. Now, a good chunk of this is my redoing a chunk of infinitary logic in a framework that made more sense to me, perhaps as a set theorist. I don't know. So a lot of it is classical results redone. One set theorist did come to me and said, after I'd published the paper, and say, oh, now all these old theorems make sense to me. So I guess, set theorists have a way of thinking about things, and maybe it's useful for other people aside from just me. But okay, so here we go. So there's an H missing. Okay, so we're going to do, this is all infinitary logic. Just I'm going to fix a few things. So we're always going to be using just a relational language. Tau is going to be a countable relational vocabulary, set of relation symbols, including equality. And for technical reasons that I won't comment on, but you may notice, there's going to be a zero array relation symbol in our language. You may see where we need that, but not really that important. I'm just telling you right away at the beginning that xi's are going to be the variable symbols, and capital Xn is just going to stand for the first in many variables. Okay, so, all right, infinitary languages. So the language L kappa aleph 0 of tau, right, is built up from the relation symbols, the atomic formulas, using negation, right? We have quantifiers as usual, exists xi for all xi, for any variable xi. We have conjunctions, right? So L kappa stands for allowing conjunctions and disjunctions of cardinality less than kappa. Now, officially, however it is that we're officially coding our formulas, we're thinking of the conjunctions and disjunctions as unordered, even when we write them as having an order. It's convenient, right? Those are more, lots of details are being swept under the rug, but that's one of them. We're also only considering formulas that have finitely many free variables in this talk. Okay, so that's our version of L kappa L of 0 tau, and then L infinity L of 0 tau is just the things that are in L kappa L of 0 tau for any kappa. Okay. All right, so I'm going to start just with the classical Scott analysis, which, I meant to look up the year. Is it from the 50s even? It might be 50s or 60s. I think it's from the 50s. Okay. So this is just the classical analysis. So if M is a tau structure, right, then for each ordinal alpha and for each finite tuple, now, okay, I think I'm tweaking the classical version slightly. I'm insisting that my tuples be of distinct elements. Doesn't make, it makes a lot of difference actually for this framework, but it probably doesn't make much difference for what people typically use it for. Anyway, our tuples are going to be injective. For each injective tuple from M, we define a size of the tuple area formula, which we're denoting as phi super m a bar alpha. And well, yes, it's going to be in, what I said is correct, in L cardinality of m plus L of 0 tau as follows, right? So this is just the classical Scott analysis, which many of you have probably seen before. All right, so phi m a bar at level 0 is just the conjunction of all atomic and negated atomic formulas satisfied by a bar in M, right? Right, where we associate a bar in order with the variables x0 up to x psi of a bar minus 1. Okay, so that's the level 0. At level alpha plus 1, what do we do, right? The formula at level alpha plus 1 for a bar is the conjunction of 3 formulas. The first one is just the formula from level alpha for a bar, which turns out to be redundant, in fact, but convenient. And then these 2 formulas, right, which actually go together. The first one says what? It's the conjunction over all C in M of the formulas for A with C appended at the end at level alpha. I mean, the formula saying there exists something satisfying that formula, right? And then the third formula here just says, well, for everything that's not in our tuple enumerated so far, right, the full tuple, when I append that variable at the end, has to satisfy one of the formulas from level alpha corresponding to one of the other points in the model. Okay, now I'm going to rewrite that on the next slide. If you're seeing this for the first time, it's a little bit confusing, but okay. But that's really the main step, going from level alpha to level alpha plus 1. And then at limit ordinals, we just take conjunctions, right? So the formula at, oh, so I did lie slightly. Anyway, I really should have said in L infinity. Okay. Anyway, because for technical reasons, it's just convenient to let this process run through all the ordinals, even though, of course, you only care about it up through less than cardinality of m plus. But, okay. At limit ordinals, we take the conjunction, but the formula for alpha bar at level beta is just the conjunction of the formulas at all the previous stages. Okay. All right. Now, I'm going to fix a little bit of notation that comes from this. Well, I'm going to redefine it later on, but just to sort of make this align with what's going to happen later, I'm going to define this set, which I'm calling E, right, of the formula at level alpha plus 1 for a bar. Okay, so the E set is literally just all the formulas for extensions of a bar by 1 point at level alpha. Okay, so that's just a set of formulas, right? It's the set of formulas for extensions of a bar by 1 point from level alpha. And with that set of formulas in mind, we can rewrite what the formula is at level alpha plus 1 for a bar, right? It's the conjunction of the formula at level alpha for a bar with the conjunction for all phi in this set. That's interesting. Why do I have, well, I have phi and psi, phi and psi. I should say psi. For all psi in the set of exists a new point satisfying psi, right? And the formula saying everything satisfies one of these formulas when appended to my sequence, right? So collectively, parts 2 and 3 just tell me what formulas at level alpha are satisfied by 1 point extensions of a bar, right? And so that's the formula for a bar at level alpha plus 1. Okay. All right. All right. I can only see Masaru and Sake and Aaron, so I hope you're all. Maybe I could expand it and see more people. Let's see. Oh, now I can see Chris and Frank. So anyway, you guys are my guide to see. Let me know how I'm doing. All right. All right. So we call this thing, right? Phi m a bar alpha is the Scott formula of a bar in M, right, at level alpha. And here's a couple facts about it. Well, first of all, right, the formula for a bar at level alpha is in fact satisfied by a bar in M always, right? Okay. Second of all, these formulas are refining. So if I have 2 tuples, I mean, 2 tuples can induce the same formula, right, at each level. Otherwise, it's pointless, right? But if 2 tuples satisfy the same formula at level beta, then they're also going to induce the same formula at level alpha for all below beta as well. Okay. And so the idea in the Scott analysis, as we'll see in the next slide, is eventually by stage cardinality of M plus, any two tuples that are going to have different formulas will have had them already. Okay. So that's the essence of what happens here. Oops, I guess I'm defining more notation first. All right. So for each ordinal alpha, I'm going to let this phi alpha of M just be the set of formulas that appeared at level alpha for all the tuples of M. The sequence of sets of formulas is what I call the Scott process of M. Now, what we're doing in the talk and in the paper is defining something called the Scott process in general for a language without reference to a model, right? But this is the Scott process of a model, right? So this is going to be an instance of the type of thing that we're defining, but just an instance induced by a particular model. And we're also going to write this. SP beta of M is just going to be the Scott process of length beta induced by M, right? So just the initial segment of this thing of length beta. Okay. All right. By the way, I should say I prepared way too much stuff, so we'll see. Let's see how far I get. But all right. All right. Now, as I was just saying, for some alpha below the successor of the cardinality of M, what's going to happen is that for all tuples A and B from M, right, if they're inducing the same formula at level alpha, they're going to induce the same formula at level alpha plus 1, right? At some stage, by some stage, any two tuples which are going to have different formulas will have had them already, right? That just says the same thing. So by that stage, if your tuples still have the same formula, then they're always going to have the same formula after that. Now, this Scott sentence, or some people say canonical Scott sentence that you see in model theory textbooks, right, is, right, officially then, when you reach that first level alpha, where this happens, where all formulas that agree at level alpha also agree at level alpha plus 1, right, then the canonical Scott sentence is the conjunction of the sentence for the empty tuple at level alpha plus 1, along with the conjunction over all finite tuples of M of the sentence saying that any tuples that satisfy the sentence at level alpha satisfy the corresponding sentence at level alpha plus 1. Now, in fact, we're going to see that there are other sentences that work just as well as this sentence. We don't really need this sentence, but that's the sentence that you usually see, or at least in the model theory textbook that I've looked at. That's the canonical Scott sentence. And then you have Scott's theorem that says, okay, well, countable Taylor structures with the same Scott sentence are isomorphic, right? So the Scott sentence, which again is a sentence in L cardinality of M plus, right, characterizes, oh, no, sorry. Well, in this case, it's L aleph 1, aleph 0 of tau. We're talking about countable structures. Characterizes countable structures up to isomorphic. Okay. All right, so now I'm just going to make one more observation about that, and that observation requires me to define quantifier depth. Quantifier depth is pretty much what you think it is, so I will just say this quickly, right? For formulas in L infinity aleph 0 of tau, right, we have the following notion of quantifier depth. If there are no quantifiers, then your quantifier depth is 0, right? And so negating a sentence doesn't change its quantifier depth, right? If you have a conjunction, infinitary conjunction or disjunction, then the quantifier depth is just the soup, the depths of the formulas in your conjunction or disjunction. And finally, if you add a quantifier, then you increase the quantifier depth by 1. Okay. Now, you could go back and look and see that the formulas from level alpha of the Scott analysis all have quantifier depth alpha. Okay. And in fact, they are the sort of the master formulas of their corresponding quantifier depth, in the sense that, right, if I have two tau structures, right, M and N, and I have tuples from those two structures, well, they could induce the same formula at level alpha, and they do, in fact, if and only if, for all formulas of quantifier depth alpha, the two tuples in the two different models satisfy the same, agree about whether they satisfy that formula or not. Okay, so the formula at level alpha for a bar, right, is just sort of the master quantifier depth alpha formula, right? Determines the quantifier depth alpha theory of that too. Okay. So I think that's, oh, I see. So in particular, it follows that we could, in Scott's theorem, right, replace the canonical Scott sentence just with the zero area formula of the sentence at level alpha plus omega, right? That does the same job, right? If I look at the zero area formula at level alpha plus omega, alpha plus omega, right? Scott rank of m plus omega, that also characterizes m isomorphism. Okay. And there are some interesting questions in it, which I'm not really talking about here about, well, maybe some earlier sentence also characterizes your formula, your model of isomorphism, and how much earlier can that happen? Right. Less than omega stages earlier. Okay. All right. Now, part of the talk is about Vaught's conjecture, so I'm going to just give a brief intro to Vaught's conjecture. Okay, so our statement of it is going to use this way of thinking of considering structures, tau structures with domain omega as a polar space, right? So, right, again, we have our relational vocabulary tau, right? The set of tau structures with domain omega, we can naturally think of it as a Polish space, right? The typical sub-basic Clopin set just says whether a particular tuple satisfies a particular relation or not, right? And that's just counting how many things you have to say, right? Which determine your structure once you've said them all, right? So that turns out to be a Polish space. Now, there's a theorem of Lopez-Escobar that says that the Borel subsets of this space are just exactly the models of sentences of L aleph 1, aleph 0 tau. Okay. Okay. So if you have a Borel subset of this space, there's a sentence of L omega 1 omega that characterizes it, and vice versa, right? A set of models of any such sentence is also a Borel set. Okay. All right. So finally, so Vaught's conjecture says that, right, for any sentence of L aleph 1, aleph 0 tau, right, if that sentence phi has uncountably many isomorphic models, then it has a perfect set of non-isomorphic countable models, right? And okay, so of course, there's an enormous amount of work that's been done on Vaught's conjecture. It's been verified for many different classes. I happen to write just one of them here, trees. And as I was saying, I think possibly before the talk started, or maybe I said it during the talk, I don't know. Part of my goal here was just to see if I could rewrite some of these proofs in a way that made more sense to me. Okay, now you're right. So Robin Knight, I guess in 2002, announced a counterexample to Vaught's conjecture, but I think its status is still unresolved. Right? I think he still claims a counterexample, but as far as I know, what I said here is it's not verified by the community, as far as I know. That happens to be the case. Okay. All right. So that's the original Vaught's conjecture. Now, you could also generalize it to analytic families, right? Borel families are just what are satisfied by sentences in L aleph 1, aleph 0, right? So you can say, well, what about analytic families, right? Analytic sets satisfy the perfect set property, so maybe, right? Right. So a natural generalization to analytic families says, well, if I have an analytic family of tau structures, an analytic subset of that thing I called S sub tau, maybe it has a perfect set of non-isomorphic countable models if it has uncountably many. And that just turns out not to be the case, however. Right? So the analytic Vaught's conjecture does have counterexamples, and these two counterexamples that I've written here both appear in that paper of Steele on trees, Vaught's conjecture for trees. Right, so he credits one to Harvey Friedman, right? Look at the ordinals of countable omega models of Kripke-Platek set theory and just look at their order types, right? He says, well, they're either alpha or alpha plus alpha times eta, the order type of the rationals, right? So exactly omega 1, many of those, right? And the second example is due to Cunin. It's the countable one transitive linear order. So a linear order is one transitive, right? Just means for any 2 points, there's an automorphism mapping that one point to the other. Okay. And Cunin's example says that, all right, well, those are all either, right, the integers to the alpha in Lex order or the integers to the alpha times, again, the order type of the rationals. So again, exactly all of one of those. Okay. So the analytic velocity conjecture is false, right? But some of the results we're going to talk about actually apply to the analytic counterexample. So it's nice to actually, know that you're applying. I mean, we're studying counterexamples to Watt's conjecture and the analytic Watt's conjecture now. In the former case, it might just be we're studying a vacuous set of counterexamples, but at least there are some examples in the second case. Okay. And so here are two, well, I called them classical theorems. They may be classical by now, I don't know. On Watt's conjecture, the first one is a theorem due to Leo Harrington, which he didn't publish, and I'm not even sure anyone knows when he proved it. It's possibly from the 80s, possibly from the 70s, which says that every counterexample to Watt's conjecture has models of cofinally many Scott ranks below omega 2. Now, that's really the theorem that led to this whole project. A number of people were interested in this theorem and didn't know the proof and sort of mentioned this to me. And then I got interested in trying to write down a proof based on some lecture notes, some slides from a talk by David Marker. And since I was a total novice, I just sort of rewrote a chunk of infinitary logic in my own way of thinking about it, so I could come up with a proof of this theorem. So in fact, a lot of what we're saying is just going to be proving that theorem. So we will sort of eventually have sketched a theorem, a proof of that theorem by the end of this talk, presuming I can get through the talk. We'll see. Let's see how far I get. Okay. The second theorem also is interesting, and we will come back to this. This theorem of Sachs from 1982 that says, all right, every counterexample to Watt's conjecture has, well, non-isomorphic countable models of the same Scott rank. In fact, you can generalize this quite a bit, as we'll see. And I don't actually recall how Sachs stated it. He might have stated it in a much more general form. We will see. But this is another target theorem. Well, we will reprove it. And then there are some interesting questions about whether we can improve it also. Okay, so, but Harrington's theorem in particular was the one that sort of inspired me to think about all this stuff. Okay, so that's part one of the talk, recapping the classical theory. Let's see how far we get with the rest of it. Okay, so this is the framework that I sort of developed to try to come up with a proof of Leo's theorem. And okay, so there's going to be a lot of definitions in machinery, and a lot of those things, I just feel like I have to show them to you to show you something concrete. But this is the one slide, or at least one of the slides that you really should, we want to take away something from it, remember things from it, as we go forward. So the next few slides are things to sort of support this slide, but this slide's important for what we're doing the rest of the talk. So, okay, so what's happening here? We're going to recursively define a class of L infinity L of 0 tau structures. The class is going to be broken into sets, right? The sets are going to be phi super n sub alpha. The super n, it just corresponds to the arity, right? What are the free variables of the formula? And the subscript alpha corresponds to the quantifier depth, or the possible level of the Scott process in which the formula could occur. So this is going to be a recursive definition of this class of formulas. The class is going to include all of the formulas that can appear in the Scott analysis of any tau structure. They're also going to include formulas that make no sense and are impossible to satisfy. All right. They're going to be big enough to include. So that's what this says here, right? Every formula that appears in the Scott analysis of any structure will be in the corresponding psi and beta. Now we're defining all of this. Again, the whole point is we're defining these things without reference to any model at all. It's all totally syntactically defined. Okay, so we're defining this class of formulas. And at the same time, we're defining these V alphas The V is for vertical. These are the vertical projection functions. And again, they're defined totally syntactically without reference to any model. And the idea is the function that we defined, V alpha, takes formulas from level beta, where beta is at least alpha, and just maps them down to the corresponding formula from level alpha. And if you think about how the classical Scott analysis was defined, it's not very mysterious how that vertical projection function is defined. You can almost just read it off of the classical Scott analysis. I mean, I will talk through it. The point is, okay, so we can come up with this recursive definition that does that. So the next couple slides are just sort of running through this definition. Like I say, it's probably just too much for anyone to take in all at once, but okay. The meaning of psi super alpha, so I mean, super n sub alpha and V alpha, hopefully. We'll stick with you. Okay. All right. All right. So how does this definition go? Well, I mean, okay, this pretty much says what you think, right? So psi n alpha is just going to consist of all conjunctions consisting of, for each atomic formula in the variables x1 up to xn minus 1, either the formula or its negation, right? We do insist, actually, because we're only talking about injective tuples, that we have the formula saying xi is not equal to xj always, whenever that's appropriate, whenever n is at least 2. All right, so that's level 0, right? Level alpha plus 1. So how do we make a formula at level alpha plus 1? But we're doing it just like in the Scott analysis. So to make a formula level alpha plus 1, we pick a formula at level alpha, phi, right? This is going to be in psi n alpha plus 1. Then we pick a bunch of formulas from box n plus 1 from the previous level alpha, and we just do those conjunctions just like we did in the classical Scott analysis. We say for all psi in E exists n psi, and also for all xn not on the tuple so far, right? The tuple, right, with xn has to satisfy one of those things from E. Now, in our case, we're not requiring any particular relationship between psi and E here. So our formulas could be total nonsense, but right, all of the formulas that really do show up in the Scott analysis have this form also. So we're picking up all of the ones that really do show up along with a bunch of other stuff. Now we want to say what okay, I have to tell you what the function V is, although it's clear what it has to be, and I have to tell you what the legal formulas are at limit stages, which is, I sort of need to define V and psi at the same time to make that work. So anyway, I apologize for the next 2 slides, and you're probably not really going to read them, but okay. Some notation, right? So remember, my size had superscripts and subscripts, right? If I drop the superscript, I mean the union over all n's, right? If I drop the subscript, I mean the union over all alphas, class, right? If I drop both of them, then I just mean the union of everything, right? All of the things, right? Now, what's the vertical projection function V alpha? Well, it's going to have domain psi beta for all beta greater than or equal to alpha, and range psi alpha. It just maps everything from one of the psi betas down to something in psi alpha. It's the identity function on psi alpha. The most important step is the successor step. Right? If I go back to the successor step here, if I map something from level alpha plus 1 down to alpha, theta from alpha plus 1 down to level alpha, I just pick that phi. That's from this definition here, right? The way I was defining theta was I had my first conjunct, which was phi. So that's just the vertical projection of theta down to the previous level, right? And otherwise, these are projection functions, right? So if I map to level beta and then down to level alpha, that's the same thing as mapping down to level alpha. And with all of that in mind, then I can say what the legal formulas are at limit stages. They are just the conjunctions of V coherent sequences, right? So, right, at stage beta, right, a formula, a legal, when beta is a limit, a legal formula at stage beta is a conjunction of formulas from all the previous levels, which are V coherent, which we're all projecting to one another, right? Which is what the real formula from the Scott analysis would do. They would all project to one another, okay? And then V on such a conjunction, if I have such a conjunction and I want to project it down to level gamma, well, it just is the formula from my conjunction at level gamma. Okay. So, I mean, understandably, that's a lot to give you all at once, but That's okay. That's the official definition, but I gave you the intuitive idea first. Okay, and then now, who knows what I'll actually be able to get to, but there is this notational convenience where I just say, okay, well, I can think about all the formulas that appeared there just as a giant class size tree, right, ordered by this relation, which is just the vertical projection relation, right? And just say phi is below psi if psi projects down to phi, right? According to, I mean, so psi, I mean, did I say it the right way? I think I did, right? My bottom function has to be in level alpha. So the higher formula just projects down to the lower formula, right? So this is a giant tree now, class size tree on all of these formulas from phi. It's just the relation of the larger thing projecting down to the smaller thing according to v. According to the v alpha, for alpha being the level of the smaller formula. Okay, and that may show up later on, we'll see. And so I drew this absurd chart. Noah saw this absurd chart presented in Berkeley. I mean, the charts are sort of ridiculous, but people have told me that it helped them, so fine. So this is how I'm visualizing the class of size, right? I mean, I imagine them sort of, right? Each row corresponds to a quantifier depth, and each column corresponds to an arity of formulas, right? So the things of quantifier depth 0, the various arities are the bottom level here. Right, here's my formula, just truth, right, from slide 1. Right, so the things in this column are all just sentences and so on, right? So I've defined now the vertical functions that just take you down in a column, right? Right, so V alpha takes you down in each, you know, you stay in the same column and project down to level alpha in this thing. So, all right, so there's a schematic of the class of formulas here. Okay, now we defined the vertical projections, and now we're going to do horizontal projections as well. The vertical projections took us down to a smaller quantifier depth. The horizontal projections just pull out some of the variables. I have a formula that's about some n tuple of variables, and I want to know, well, if I just look at some subset of those variables, what does the formula say about them, right? And you can syntactically extract that as well, right? Actually, I defined this slightly differently than I did in the paper in ways that aren't really that important. So IMN is going to be the set of injections from m to n. Little I sub n is the identity function on n. We have the notion of a subtuple induced by one of these injections. So if I have something of length n, and I have an injection j from m to n, right? There's a subtuple induced by that injection. I mean, it's just sort of what you think it is, right? In the 0 place, I just look at the index that j gave me and so on, right? But now I'm insisting that j is an injection. So if this is a tuple of different things, then this will also be a tuple of different things, right? I mean, but the order can be totally scrambled, right? It's just not really clear what that means. Okay, so each injection from a possibly smaller, I mean, it could be the same integer. It could be a permutation of n, right? But each injection from an integer less than or equal to n induces a subtuple, possibly, you know, reordered subtuple of the original tuple. Okay. All right. So with that in mind, we have the horizontal projection functions. And so it's, you know, analogous to the vertical case, except now I just have one function h instead of v alphas for each alpha. Okay. But h takes in 2 arguments instead of 1. It takes in a formula and it takes in a injection to the index set of the number of the variables of the formula. Okay. All right. So if phi, right, is an n-array formula, j is an injection from m less than or equal to n, okay. All right. Then h, well, h again, it's going to be defined on everything from c, right? When I think about it on formulas that really do occur in the Scott analysis, right, what's it going to do? It's going to take the formula for a bar at level alpha from the Scott analysis, and it's going to extract the formula for the subtuple of A bar induced by J at level alpha. Right. And again, you can define this recursively, but syntactically. So it's just a formula that extracts the piece of that formula, the formula for A bar at level alpha corresponding to the subtuple B bar at level alpha, where B bar is the subtuple induced by this injection J, like this. And again, okay, so this is the meaning to hold on to. I'm gonna run through the actual definition too quickly, but it's just a recursive definition, right? I mean, the idea is at level 0, right? Okay. The formula level 0, remember, was a conjunction, right? I mean, it was a conjunction for each atomic formula of either that formula or its negation. So how do I extract that according to J? And so here's phi. So H phi of J is the conjunction of all conjuncts of phi, first of all, whose variable indices are contained in the range of J. If I take the conjuncts, or all the variables in that conjunct are indexed by things in the range of J, and then I should replace, right, X sub Ji with Xi, and that gives me now a formula, right, of the right arity, of, I mean, whose variables are indexed by the domain of J. Okay. And the other conjuncts, we just ignore them. Okay. And when I want to define this thing at level alpha plus 1, well, okay, this takes a bit of unpacking, but I have a formula on level alpha plus 1. I'm going to horizontally project it. What does it take to determine a formula level alpha plus 1? I need to know its first conjunct, which is just its V alpha value. And then I need to know what its E set is, right? And those two bits of information determine a formula level alpha plus 1. Okay, so if I'm defining, so I'm defining this thing H phi J. I need to know what the V alpha of it is. Well, in fact, H and V are going to commute, right? So V alpha of the H of phi and J, right? I can figure out by first projecting phi down to level alpha and then applying J. Okay. Now I need to know what things are going to be true about 1-point extensions, right, of the thing I chopped down to, right, here, my M tuple. Well, all I do is look at, well, so this is a little bit involved, but I'm starting with a formula of arity N. So here, the E set of that formula, it told me what things were satisfied by 1-point extensions of that. Well, all of those additional points are 1-point extensions of my tuple of length M. So, okay, so I have to sort of horizontally project down all of the things in E of phi, right, according to injections where, well, I have the injection J, which I'm working with, plus I can add one more point. So I can send M, the new index, to anything from the index set of this, the E set of my original phi that I'm applying this to. Okay, and again, that's really the main point. I mean, the last thing is just, if I am projecting down horizontally from a conjunction, will I just take the conjunctions of the horizontal projection? Okay, all right. So, I mean, understandably, that's too much to actually grok all at once. All right. So with that in mind, you can, or with that in hand, not necessarily in mind, you can then define the class of sequences of sets of formulas. And there are 7 axioms, which I will sort of run through kind of quickly. Okay. All right. So what we're defining is the class of Scott processes in general. So a Scott process in general is a well-ordered sequence of sets of formulas. Each set of formulas, phi alpha, comes from the corresponding psi alpha. The sets of formulas have to be closed under permutations of the variables, of course, because the model doesn't come with any particular order. Okay. And all right, so, I mean, these axioms mostly say just what they have to say. For any formula level alpha plus 1, the E set that built it had to be a subset of level alpha. right? The set of formulas that appeared on level alpha has to be the downward projection of every set of formulas that appear on each subsequent level beta. Also, the formulas that appear in any box phi m alpha in this Scott process have to be the leftward projection of the things that appear to the right of it in that process. Okay. All right, and there's a couple axioms about the promises, which I called the coherence conditions, which more or less say your promises have to be coherent, right? So if I say for a given phi what things are satisfied by 1-point extensions of me, and then I go up to a vertical projection, right? There has to be agreement about what is going to hold, what's going to be satisfied by the 1-point extensions as promised by higher formulas in the sequence. These two conditions, I mean, essentially say that, but they apply in slightly different contexts, right? You sort of have a limit case in a. All right, and the last formula just says, the last condition just says that, you know, everything is supposed to be in the same model. So if there's a formula satisfied by one tuple and a formula satisfied by another tuple, well, there has to be a formula corresponding to the two tuples joined together, right? So if I have a formula phi and a formula c, right, then there has to be some other formula that projects horizontally down to both of them. Okay, so if I have a phi, n tuple phi at level alpha and an m array c at level alpha, then there has to be an n plus m array formula at level alpha, which is just basically subsuming both of those two things. Okay, which projects, it projects horizontally down to each of them. I mean, since the formulas are closed under, class of formulas is closed under permutations of the variables, you might as well let one of those induced injections be the identity function. The other one can be an arbitrary injection. Okay, so I mean, the point of this was that's just an axiomatization of a class of well-ordered sequences of sets of formulas coming from these C alphas, and they're supposed to be capturing the class of Scott processes of, I mean, the class of sequences of sets of formulas that come from the Scott analysis. And well, okay, we'll see to what extent it actually accomplishes that job. I wanted to throw in one set of definitions first. Okay, maybe I'll pause for a second. I mean, I'm running way short on time, but all right, just seeing who I can see here. All right. One last bit of definition, notation before I talk about what extent this definition does what it's supposed to do. All right, so the rank of a Scott process, right? Remember the Scott rank of a structure, right, was the least level alpha where any two tuples which satisfied the same formula level alpha satisfied the same formula level alpha plus 1, which really just means that the vertical projection function was injective on level alpha plus 1, right? So we can make that definition for Scott processes in general according as defined by the axioms that we just gave, right? The rank of a Scott process is just the least alpha where the vertical projection function down to level alpha on level alpha plus 1 is injective. It doesn't map two things from level alpha plus 1 to the same thing at level alpha, right? If such an alpha exists, right? So we can define the rank of a process, and you can prove from the axioms that when that happens, then the alpha is also injective on phi beta for all subsequent beta beyond alpha plus 1. Okay. Now that's defined in analogy with what happens in the classical Scott process, and fortunately, I mean, the point is the two things agree, right? If M is an infinite tau structure and we run the Scott process, the classical Scott analysis we talked about at the beginning, then that sequence of formulas as defined in the beginning does satisfy the axioms that we just said, right? And the Scott rank of the structure M is always just the rank of the corresponding Scott process as defined right here. That really is just the level where those projection functions become injective. Okay. So again, the point of the axioms is to just describe abstractly sequence of sets of formulas that can show up in the Scott analysis of tau structure. All right. Okay, so a tau structure M is said to be a model of a Scott process if, well, it literally is just an initial segment of the Scott process of the structure. So if P is the Scott process of M up to level alpha for some alpha. And so the next sentence that's written here says that the definition captures what it was supposed to capture as far as countable length Scott processes are concerned. The Scott process, well, right. I guess I said what I meant to say. The Scott processes of countable length with all levels countable, meaning having countably many formulas in them, are in fact exactly the initial segments of the Scott processes of countable tau structures. Right. So as far as countable structures are concerned, the axiomatization does what it was supposed to do. Okay. The big question here is, what about Aleph 1, right? And we're gonna, so I'm stating it here, and then I'm gonna sort of, well, how much time I have, but I'll talk about some of the issues involved in a second. Right. If I have a Scott process of length Aleph 1 according to my definition, right, is it in fact the initial segment of the classical Scott analysis of some structure of size Aleph 1? Right. That's something I don't know, and it really could go either way. I don't know what to think. I'm going to sort of talk through some of the issues, right? But it's a totally wide open question. Now, in fact, the answer is no for Aleph 2. There's a theorem which, well, in one community is always called Hjorth's theorem. But then someone pointed out to me that the theorem also exists in older papers of Laskowski and Shala. So there are theorems to Hjorth and also to Laskowski and Shala, which show that this doesn't, well, work. I don't know if it's a defect in the theory or not, but it doesn't work for Aleph 2 in the sense that there are provably in ZSE Scott processes as defined just now of height omega 2, right, which will be the initial segment of Scott analysis of some model in some forcing extension, but for which there's no such model in the ground model, right? So, you are, of course, certainly, because any set can be made countable, the models of the theory, and the Scott processes abstractly defined, are the initial segments of the Scott analysis, the classical Scott analysis of structures in some forcing extension. That certainly is true, because you can always force to make everything countable. But there may not be a structure already in V whose Scott analysis gives you one of these Scott processes. And so for Aleph 1, I don't know. I don't know if you can define a Scott, you can construct a Scott process as we just defined of height omega 1 that doesn't actually correspond to an existing model. Okay, now the next thing I wanted to do is run through essentially some of the ideas behind what is on this slide. And there's really two cases to think about: Scott processes with which have a last level or don't have a last level. So here we go. So the first thing is successor levels, right? Suppose I have a Scott process. Okay, the theorem here says every Scott process of countable successor length with all levels countable has a model. Now I put successor in parentheses because, as we're going to see, that the theorem is true with the word successor removed, but I'm just not going to prove it. I'm going to prove it in the successor case, and then we will see that it suffices to consider the successor case in a second. Okay. But so here's the sketch. Here's the idea is, now let's suppose we have a process that's of length delta plus 1, right? So phi delta is the last level. It's countable, right? And we want to build a model that satisfies, build a model whose Scott analysis is exactly the set of formulas that we have, right, sitting in front of us. Okay, well, the model is going to be a countable model. So we're just going to let the domain points in the model, we're going to label them as Cn and an omega. And now we're just going to run through level delta. And for each initial segment of this sequence of points, domain points Cn, I'm going to choose the formula phi n. Now, when I choose it, what does that mean? Really, I'm just assigning it this formula. As I'm building the structure, the only thing I get to do is say which relation symbols the tuple satisfies. Now, when I choose phi n, the formula phi n projects down to level 0. I should have written, well, first of all, I have m and n representing the same. Okay, my m's and n's are kind of wild here, but interesting. All right, I guess this should say phi m, and that should be an m, and this should be an m plus 1. Okay, well, we will get it straight. When I choose my formula, which should say phi m, I can project it down to level 0, so that should be v0 of phi m, and that tells me which relation symbols my tuple is going to satisfy in my construction. Now I'm walking through and doing this for each C initial segment of length m, and when I do that, I'm going to make my formulas horizontally project to one another via the identity function. So the horizontal projection of the formula for length m plus 1 is going to be the formula for length m. Okay, well, I certainly can do that. That's not a problem. The axioms say I can do that. Now I'm hiding some details. By suitable bookkeeping, I can ensure that actually the tuple of length m really will satisfy phi m in the corresponding structure. That sounds like a lot of magic. In fact, things are very simple in the case where delta is also a successor. In the case where delta is also a successor, I don't actually have to think about the whole Scott process before that. All I have to do is keep my promises from the level before. Right, so things are simple. I mean, in the limit case, I really do have to worry about all the different levels, but in the successor of a successor case, all I need to do is ensure that every time phi n makes a promise, i.e. there's this formula psi that's in my existence set for phi n, eventually I have to pick a larger phi m, right, which projects down, which when projected down and then horizontally projects over to this formula psi like this. And this is, when you unpack the definition, is just what, exactly one of the axioms of a Scott process. Okay, so things are slightly more complicated. I mean, I'm hiding lots of details anyway, but I'm actually not really hiding any details in the case of a successor of a successor. That's really all you have to do, I mean, everything else works out magically by induction. So as long as I maintain that one condition, the model I build according to this process just satisfies all the formulas from the Scott process up to that point. Okay, so that's a quick sketch. I mean, the successor of the limit case of limit ordinals is a little bit more complicated. Okay. Now, all right. And I'm totally gonna run out of time, but let's see. I have 3 minutes or something. I mean, a lot of mysteries are right here in what we just did. We just showed how to build a structure, but there are lots of mysteries regarding just how much control we have over what that structure is like. It's not hard to characterize. We can see it. When the structure we build actually has rank at most delta, that is something you can see. But suppose you don't want it to have Scott rank at most delta. How much freedom do you have to build a model of a larger Scott rank? I mean, if you don't want the projection functions at the next level to be injective, how much freedom do you have to make that happen? And this is, I almost feel like this is where the whole mystery of Watt's conjecture is. This is something very strange, and probably, they're just, this is a mystery that can be unraveled by making additional assumptions about what this level looks like. I mean, okay. So I mean, anyway, this is I think that where a lot of the deepest mysteries are. Just when you try to construct a model there, how much freedom do you have to design the Scott process at the next level there? Okay. And actually, I said it right here. This is an explicit version of what I was just saying, right? If you're given a Scott process P and it has a last level delta, and really I'm thinking about phi delta as being a countable set. and delta being countable, right? So let me just see what I said here. And given a Scott process, I have a phi that's at level, right? It is in box n+1 of level delta, right? When can I find I build my process so that at level delta +1, there's a psi at level delta, which is projected down to by phi, right? But I omit phi from the promise set, from the E set of psi, right? Or conversely, just when am I forced to pick up that promise? Anyway, so this is one of the key sort of mysteries in this process. Okay, I'm desperately low on time. How much time do I actually have? Like 2 minutes?
Well, I think you have started your talk 5 minutes behind the schedule, so at least you have 5 minutes more.
Okay, all right. So I'm just going to whip through the remaining 40 slides in about 5 minutes, and we will see what I can say. So what was the point of just what happened there? It was to show you building a model from a Scott process with a last countable level, right? The other half of this, oh, there's just way too much to say, isn't there? Okay, I did say that you can, that the ability to build something of Scott rank at most delta is not mysterious. And this is this property here, which I'm calling amalgamation, which just says that basically amalgamation is the property of not having incompatible horizontal extensions. So your level delta amalgamates if whenever two formulas on level delta have the same leftward projection, according to the identity function, there's some other formula theta, which projects down to each of them, right? Which is also the identity function on the first n variables. What is this amalgamation saying? It's saying that really things that satisfy this formula can't have incompatible extensions, right? Okay, so level delta sort of amalgamates if whenever two formulas project horizontally the same thing, there can be some other formula that projects down to both of them. And this is the condition, I think I say it right here. Amalgamation is the condition that lets you terminate your process, basically. It just is what lets you build the next level in such a way that the vertical projection is horizontal. Just lets you have each formula at level alpha have a unique successor at level alpha +1. Right? I mean, if you had a failure of amalgamation, then you're just definitely not going to be able to do this because you're going to have different types. Right? This formula is going to have two extensions that can't be realized at the same time, and so the things that satisfy those two extensions are just going to induce different formulas at the next level above this formula. But if that doesn't happen, then you can terminate the process at that level. Okay, so let me try to blow through the rest of what I had here in whatever it is, 2 minutes or something like this. One question is, well, okay, what about at LF1? Can you do this at LF1? This is essentially Harrington's proof. I put a little star there just because obviously he didn't state it this way. If you have a Scott process, if you just map everything up to LF1, so you have a process of length for the cardinality. The length has cardinality L1 and the last level has size L1. Can you build a model? Well, you can if you have this amalgamation property that I just defined, and that really is what's in Harrington's proof. But can you do it in general? This is very strange, right? Can you drop amalgamation from this and still prove that? Still build a model without amalgamation? I don't know. I don't have any idea how you would, but we can amalgamation slightly. That's something that I could say eventually. All right, so now I'm just going to have to give you a really high level tour of what was left. Okay, so I just did successors and processes with the last level. You can also look at the processes of limit length, right? You can run through this and say, well, if everything is countable and the process has limit length, then you can build a next level to go on top, right? And that's why reducing to the case of levels with processes with the last level wasn't really a reduction. We did this before because if you're of countable length, you always can extend. But what if you're uncountable, right? If I have a process of uncountable length, uncountable limit length, can I always extend it? Can I always stick a new level on top? Maybe not. And actually, I stated it in a more concrete way here. Here's a question. Just says, suppose I have countable tau structures, M alpha, alpha less than omega 1, and suppose that their Scott processes are coherent. So for all alpha below omega 1, the process of m beta up to length alpha is the same for all beta greater than or equal to alpha. Right? So I've got an omega 1 sequence of structures, and for each alpha, all of my structures have the same Scott process of length alpha. For all the models indexed at alpha and later have the same process up to length alpha. Well, does there have to be a structure whose Scott process is a coherent part of all those individual Scott processes from those models? And by what I just skipped over, the answer is yes, if this was all countable. But at length aleph 1, I don't know, right? Can you sort of coherently glue together omega 1 many countable models to a model of size aleph 1 that whose Scott analysis agrees with the initial segments of the members of your sequence? Okay, so that's one mystery. All right, there's a whole. It's okay. So that was supposed to be part 3 of the 4-part talk. The rest of the talk is all about Vought's conjecture. I'm going to skip just way. I'm basically out of time. There was one new theorem I was going to state, and all I'm going to do is just show it to you and just say that it actually just follows. Well, okay. Let me say a couple things about this theorem. One is I was completely sure at the time, and I'm only like 85% sure now that this theorem is not new, even though I asked around and everyone told me they thought it was new. So I don't know. If any of you knew this theorem before, and you say that, I believe you. But the people I asked said they didn't know it. And so what does it say? It just says that if you have a counterexample to Vought's conjecture, the analytic Vought's conjecture, for which we know that there are counterexamples, if we look at the models of that counterexample of Scott ranked aleph 1, well, okay, so what does it even mean? Right, there are models of size omega 1, which will satisfy the analytic definition after we collapse omega 1, right? We look at those models, which happen to have Scott rank aleph 1. If there are only countably many of them, then in fact, you can reflect that down on a club. So for club many alpha below omega 1, there will be exactly the same number of models of those Scott ranks, of club many Scott ranks below. And it's literally, you just put everything in an elementary submodel and collapse it. So the point is just the models you get, the actual models of rank aleph 1 really have to just collapse to all the models of each Scott rank alpha when you collapse an elementary submodel, right? It's really very simple. There's a little bit of work to show that, when you collapse it, you do get distinct models, but you have to argue that there weren't any other models that your collapsed elementary submodel didn't see. But in fact, that doesn't happen. Anyway, I'm sorry that well, I went over and I just basically skipped the last quarter of my talk anyway, but all right. Anyway, Sakai, congratulations, and I hope to see you in Kobe soon. So thank you for including me. Thanks.
Okay, thank you for the talk.
Right.
Are there any questions or comments? So first, Ellie, you can go ahead.
I don't know.
No?
Well, many. Oh,
I see Sakai raised his hand.
Sakai, so first, yeah. Sakai, you can go ahead.
Oh, there we go. There's the chat. Oh.
So I have two questions.
Yes.
Perhaps very, very stupid one, but I'm entitled to ask.
Please, yes.
Stupid questions as far as my name is mentioned. So one of them is it easy to construct Scott process who does not have any corresponding structure without collapsing omega 1, for example, in the generic extension.
You're right. No, that is sort of, yeah, right. That really is the idea, right? Is you take these, yeah, you basically feed in a collapse. Well, yeah, you feed in a bunch of collapses that show that you're, explicitly show your structure can't have cardinality greater than L(1), right? But you can still build the Scott process for these. Yeah, that's exactly how these examples go. But yeah, those are the only examples I know of.
CCC extension and some other.
Yeah, no, I don't know how to do anything like that where it's a forcing extension where you don't just collapse.
So there are many open things in this area, right?
Right. No, that's right. I mean, yeah. So one of the things I was trying to get to this and didn't really quite say it is can you take like an Ehrenstein tree on omega 1 and just code it into a Scott process? Could you actually make up a Scott process whose induced vertical projection tree really is
just the theory of trees in some sense, right?
Yeah, right. And so maybe I don't see how to do it, but maybe you can just copy an Ehrenstein tree into a Scott process of height L(1), right? That would be great if that can be done.
Yeah. So another question. You considered L infinite omega.
Yes.
But can you do something similar in L infinite kappa?
Right. No. Yeah. Right. Probably you can, but I haven't. Yeah. Right. So that's another really interesting direction to go in that I just haven't thought about. But yeah, it should be possible, and it should be interesting also.
Yeah. Okay. I mean, so many things are still open.
I was talking with Saharan just recently. He was saying that he has a paper in the capital of Georgia. I don't know how you pronounce it, Tbilisi, right? He has a paper in the Tbilisi Journal of Mathematics that's in this direction, according to his description of it. But when I tried to find it on the archive, I actually didn't find it. So I'm not really. There is a paper that was published in that journal, but it didn't obviously match the description he gave me of it. But whatever paper he was describing sounded like it would be exactly that, in exactly that direction.
Okay, thank you. Thank you.
All right, yeah.
Next address, do you have something to say? Please go ahead.
Yes. So thank you very much, Paul, for your lecture. And there are, very early similarities between these Scott processes and, well, perhaps not the projection functions, but somehow the idea behind this, and the quite recent, axiomatization of abstract elementary classes that we got with Scheller. It's a short paper, and at some point, what we built as a sentence to axiomatize an abstract elementary class, so to get the definability, is a kind of simulation of something similar to what would be a Scott process in a situation where you only have your class and you're trying to mimic the system of possible embeddings. And this, this is layered by ordinals, just like in the Scott processes. It starts exactly the same way, and so it goes all the way through. Now, connected to Sakai's second question, this turns out to give you a sentence in L, some large cardinality, around
I see.
And kappa plus. So the second parameter is not omega. The second parameter is something beyond omega. It's interesting because it doesn't. Abstract elementary classes don't define well ordered, so it cannot be really L like L omega 1. It's too powerful for that. Yet you have something in between. These are sentences that look very much like the Scott processes that get your axiomatization of an AEC. Yet they are, they cannot be as wide as that because L omega 1, the sentence defining well order cannot be there.
Right. Wait. So what is the paper? Can you tell me the number or the title or something?
Well, it's infinitary logics and abstract elementary classes.
Okay.
And it's so it's Scheller and myself.
Okay.
So I can send it to you.
That'd be great. Please.
Yeah, there are many of your questions before you started speaking about the Vought conjecture are kind of I've been looking for examples of high length high complexity abstract elementary classes that might be similar to this. I don't know about analytic versions or anything like that.
Right.
But it all seems kind of in the same neighborhood. And also Sakai's second question that, so thank you very much.
Right.
Yeah.
Right. No, it's
Yeah, we
interesting.
should.
No, I'd like to
Is
take a
that
look.
okay? Is that okay?
Yeah.
Yes.
Any other questions or comments? If not, let's thank the speaker again
All right.
and close this talk.
Thank
Yeah.
you. All right. Thank you very much.